In this video, we're going to look at something called Dalton's law of partial pressures. So John Dalton actually studied how multiple pressures of different gases would collectively characterize themselves in a single container. And what he was able to figure out was that the total pressure of a mixture of gases that were acting in ideal conditions is equal to the sum of each individual gas's pressure. And so this can be shown in this equation here, where the total pressure is equal to the gas, say A plus B plus C, all the way to however many gases you have. And an example here shown that if you have gas A that it has 300 kilopascals of pressure in a separate container of another gas 600 kilopascals, and then a third container of 450 kilopascals, if you were to combine all of those into a single container at the same volume, then their pressure, total pressure of the entire system would just be the sum of each individual's container. Now, one thing that you need to keep in mind is that there are some additional things that we're going to look at, but for those mixtures to be true, there can be no reaction between those gases. So that's one particular caveat or a condition that must also be met for this to work. Some other pieces of information that we're going to look at in addition to that is that the partial pressure of a gas is related to this concept we studied several chapters back called the mole fraction. And if you remember, the mole fraction is where you take the moles of a particular substance, like you have over here mole A or N sub A, that's the number of moles of substance A, and you divide that by the total moles in an entire mixture, and you get this kind of variable or value that has no units that we call the mole fraction. And it turns out that if you take the moles of a gas and calculate the mole fraction in a mixture, that you could do and calculate the same exact value if you use the partial pressure and the total pressure of that system as well. So if you took the pressure of gas A and the total pressure in the entire system, and you divided the total pressure into the partial pressure of A, you would also get the mole fraction. And in a roundabout way, what this really suggests to us also is that the total moles of a mixture of gases can be calculated also as the sum of all of the individual moles within a mixture of each gas. And so keep in mind that we could potentially need this particular equation here. This is the partial mole summing up to the total mole. We might need the mole fraction calculated using moles. We might need the mole fraction calculated using partial pressures. And we could potentially need the equation of partial pressures of individual gases. So what we're going to do here is we're going to use each of these particular points of information and potential uses of the partial pressure of gases of Dalton's law, and we're going to try an example problem and see if we can solve it using all of these pieces of information. And so this particular example says you have a 36.0 liter cylinder, so there's your volume, of a gas used for calibration of blood gas analyzers in medical laboratories containing a couple of different gases. In fact, it tells us the mass of those gases: 350 grams of carbon dioxide, 805 grams of O2, and then 4,880 grams of N2. And it says at 25 degrees C, what is the pressure in the cylinder in atmospheres? So they're actually asking us pressure in a particular set of units. And so let's just look at this. We're not changing conditions or anything like that, so we won't need the combined gas law. We will need the ideal gas law here. But let's see what we have. Pressure, volume, moles, R, and T. And let's see what we have and what we don't have and see how we need to get there to get everything. So we do have to have volume, that's 36.0 liters. And we're actually calculating pressure, and we need to calculate that in ATMs, so that's one thing. That means our R needs to be our 0.08206 liters ATM per mole Kelvin unit. Our temperature says 25 degrees Celsius, which means that's 298 Kelvin. And what about our moles? We weren't given anything specifically in the value of moles, but we were given mass and the formula of each one of those. And it turns out we will be able to calculate the moles. So we could calculate the moles of CO2, moles of O2, and moles of N2. But what this number needs to be is total moles. So this needs to be total. So before we can calculate this, let's figure out how many moles we have of each gas and then sum them up. So we have 350 grams of CO2, 805 grams of O2, and 4,880 grams of N2. So let's figure out their mole value. And so we'll divide each by their respective molar mass. For CO2, that's 44.01 grams is equivalent to 1 mole. And that value to 2 sig figs calculates to be 8.0 moles of CO2. We will divide by oxygen's molar mass of 32 grams is equivalent to 1 mole. And that gives us 25.2 moles of O2. And for nitrogen, we'll divide by 28.02 grams is equivalent to 1 mole. And that'll give us a value of 174 moles of N2 to 3 sig figs. And so we know each individual mole value. Let's sum that together to get N total. And so I sum that together and round it to the appropriate sig figs, and it ends up being 207 moles total of all of our gases. So that means that that's that value here. So this is 207 moles total. Moles. So we can plug this into our calculator, into our equation, of our ideal gas law. We're going to solve for pressure, so that means we're going to move that V over into the denominator, and we can plug everything in. So this is 207 moles R. Always important to keep writing your units to check whether or not you're doing your solving of equations correctly and putting everything in the proper units. Sometimes if you don't change a value into the proper unit, you won't know unless you're writing your units down, so you need to write them down. The volume will be 36.0 liters, and just check to make sure your units cancel properly. Moles cancels, Kelvin, liters, leaves you with ATM, which is what we're solving for. And we plug this into our calculator, and I get a value of approximately 141 ATMs right here. So this is how you use the ideal gas law along with Dalton's law of partial pressures, which also includes the use of, different mole values. You could sum those up as well. Now, this is not the only way that you could do this problem. Again, you could solve using the ideal gas law. So this is an alternative, just very quickly. Is you could solve for the pressure of CO2, the pressure of O2, and the pressure of N2 using each individual mole value you could plug into that equation here. Solve for the individual pressure and then just sum those up to give you P total. If you do that way, I promise you'll get the same answer here. So it's whichever method you prefer to use, and it's whatever kind of works for you. So again, this is Dalton's partial pressure law and the use of the ideal gas law.